In today's video, we're going to talk about design principle using Go. These are not just any design principle, these are the most fundamental and crucial design principle that we should be using day in, day out while achieving the business requirement, because at the end of the day, it is the outcome that matters. So let's get right into the video without wasting much further time. So first in our list is dry. Do not repeat yourself. This principle is about eliminating code duplication by creating reusable function. So let's take an example to understand this statement. Over here we can see we are taking the name and age and we are printing name and age of a person. Another person, same thing again and again. We are repeating three lines. Now we have 100 per people. We'll repeat this 300 times. So very bad thing. What we can do? Easy. What we can do? Make a function that takes name and age, and we can iterate over these 100 people name and age and quickly print it using this function. That is, you can do with much ease. This is what dry principle is. That's it. But let's take example how we will use Go. I'm just taking an example because we are implementing using Go. You can take Java and anything. You can take it as an assignment, whichever language you are most comfortable with. But over here we are using Go. So let's use Go. How we'll be using Go to have a dry code. So over here you can see we have a person struct. There we define what property this person will have. Let's take example, if you want address also, you can add address also. So that's much better way of handling the code, handling all the property related to the person. Now let's move to print person function. Over here you see it accept a argument of type person, and because of this we can handle all the properties of a person. We don't have to define many arguments, name, age, then address. Everything is handled by this just one variable. So another tweak of dry, you can see we extended it just not for the function. We even saved this argument, number of arguments. So what we are doing over here is we created a slice or array, in other words, if you can, array of object of type person. In Go we say this slice, and we iterate over it, and we just print easily the name and the age using the property p.name p.age. So this is how it's done. This is most used principle you will find at work, because first, it is easy to maintain, extendable, and you can see how easy it's to even comprehend what code is doing. So yeah, this is most used principle, and even some variation of this could be because you are making a function out of a repeatable code. But sometime I have seen what happens is, let's see, you have a function called citizen, and over there you have some code that says checks if you are local or not. But instead of writing in these lines of code this code in between, what we can do is make function have is local. So how it this helps is, let's take you have a prod bug. Now you have to resolve in within 30 minutes because it costs money, and business is the key thing that we should be looking forward to, because this is from where you will get the money. You want to get it this fixed quick. Now if you would have written function like this is local, you can skim the code very fast. So this is just another variation of dry. So this will help you in more ways than you can think. So second in our list is YAGNI. You aren't gonna need it. So this principle advice that not to add functionality until it is necessary. It keeps code clean, simple, focused, and on current requirement. So let's take example to understand this statement. So let's say we have a requirement to calculate the area of a circle. So we implement it We implement interface also to make it generic. And now we implemented square also. But is it square required? Let's say this square code itself is taking 2 days, and circle code in itself take 2 days, 2 days, and we made it generic. We made an interface that's an add-on, and our requirement basically just want in 2 days or 1 days. We want it quick. So if we don't know, in this case we can see that we would require other shapes area also. But let's say you are not able to think that much far, and still you are pushing for something generic. But in a foresight of even year or so, and in 6 months, if the requirement comes, would we not able to do it? I think so, we would be able to do it. But if we put much efforts on implementing now rather than 6 months later, that is not a fair trade. We should keep it simple, keep a good code, and deliver. So if we imply YAGNI, keep it simple. So this code would look like this. We wanted area of circle, we implemented the area of circle. That's the thing. Because there can be many variables. In this case, we are able to decide the interface, but who knows? There are many things. This example may not be able to cover, but I have seen there are requirement if there is money involved and we need quickly. So we try to take that step which can be done in now, and we'll take it afterwards. So, and also in software life cycle we have iteration. We'll get another chance to make it better. So it's not like just now we have to make it better. They'll get another chance. So this is more of a outcome based principle, that you should achieve outcomes rather than just make it generic, adding more code that it's not required for now. Maybe in future we'll get time also. So that is Yagini, you aren't gonna need it. Third in our list is KISS, keep it simple, stupid. This principle emphasizes writing simple and straightforward code instead of over engineering. The goal is to reduce complexity and make code easier to read, maintain, and debug. So let's understand this statement with an example. So over here, we are checking if this number is even or not. So what we do, we send that number in the argument, we convert it to the string and check if the last character of that string contains 02468. If that's there, then true, else it's false. So you would be thinking it's kind of overkill. If we follow this principle case, then you would do something like this. Just a modulus operator. If the remainder is 0, then this is much better than this. This is kind of over complication of finding a even in the work I have seen. There was one case that, yeah, we could have done recursion over it, but iteration was also possible. We choose iteration. Why? Now let's take an example. If if you are handling something on call, you have some bug in production, you have to resolve it quickly. Thinking in that way, which one would you prefer, recursion or iteration? I would say iteration, because in industry we use logs to check. Our code is not just some few lines that we can debug, and that too it is running in production. So You have to debug and skim the code and understand it on the fly. And if you encounter recursion, then it is difficult. Iteration would be better. Recursion, try to avoid it if you can. If you can do it with iteration, it is easier to debug and just to think about it. Recursion can become overwhelming if it's a good code written in a recursive function. Good amount, let's say 150. 150 lines of code is there, so many computation are done. So then it is little difficult to have it, and also kind of overwhelming when you are in such a tough situation. So keep it simple is a better thing, because if you can achieve the same thing and it's not that way apart from time complexity wise, space wise, then choose simple. And also doing something like this is difficult, because in this case it's easy, but making something easy enough, because there are answer lying around, you can implement things easy enough, as in using already knowledge that you have, or already written code, and making use of them instead of writing something new and then implementing the same. So making things simple is kind of difficult, because you have to think about it, iterate over it, how to make it simple, how to make it condensed. Because if you can make a complex topic easy enough to explain, then you know that topic much better than explaining in jargons and everything. So this is not easy. In this example you can see it's fine, but making something complex and making chunks which are digestible in nature is way difficult. So it is kind of a thing that can be done by a good developer, a good coder. So yeah, so this is third principle, kiss, keep it simple, stupid. Now coming to our fourth and the last principle, solid principle, the most known, most asked principle in interviews. So let's discuss it. It's a acronym of five design principles that make code more understandable, flexible, and maintainable. So let's see. Let's handle the S of this acronym solid. S stands for single responsibility principle. So what does it says? A function class method should have only one reason to change. It should do one thing well. It's not like it could do many things, but it should do one thing, because in the time of debugging, in the time of reading the code, in the time of understanding the code, it would be much better if one function do one thing, because it will make the code predictable and understandable. So let's take example. So in this example you can see we have a save function. What the same function does is saving the name and the email of a user in the database. Let's take example. Or over here we are printing that you can see saving user to the database. Let's say it saves, don't worry about the code. You see over here that we have name and email and we are trying to validate it, but this save function should just save, not validate it. What could be better is we have validate function, then save function, validate function, then save function. This would be a much better approach, because this function is doing just to save data in the database. What this function is doing, validating the data that should be stored in the database. So this has one work to do and this has one work to do. And over here this method is doing two functions, validating and storing in the database. So that's not good. We have to follow this principle, single responsibility principle, SRP. When we follow this SRP, so as discussed, we have now a validate function and we have a save function. That's how we are doing. We have a validate function, we have a save function, and you can see over here we are validating. If it's not an error, we go over here and save. We have two things that are handling our workflow: validate, save, and in two different methods, two different contexts, so that will not overlap. Now moving to the O of solid. O stands for open closed principle, OCP. The entity should be open for extension but closed for modification. You should be able to add new feature without changing the existing code. So let's understand these statements with an example. So over here we are calculating area according to the shape, and you can see the shape type is int and we are defining it sequence wise. 0 for circle type we have given 0 and rectangle 1. This is a syntax of Go to define it in a sequence manner, giving basically initializing it 0 1. You can check online. Now, and we have a struct of shape where we define the properties type, radius, length, width. Okay, radius for circle, length for rectangle, width for rectangle. Okay, that's fine. Everything is fine. Good. But now if we want another, we want square, then how we will accommodate? We will not be able to, because you see we have defined just cases for two, circle and rectangle, and default returns to 0. Now if we follow open closed principle, what we'll do is we'll create an interface helps us in defining the function signature, what function will do, not how will it do. So we define what it will do, instead defining how, like we did over here. What we are going for, what it will do, area, it will calculate area. It will not, it is not saying how is in our hand. So we defined a circle, we add a method to it, and this is how area of circle is defined. This is how a area of rectangle is defined. If we want to add triangle, this is how area of triangle is defined. It's not just sticking to just one method calculating area, and there we are taking decision according to the shape type. We are defining what and how at one place, what we are defining at other, how is according to the requirement. And you can see over here we are able to print the area. This is basic. Coming to the L of solid, Liskov substitution principle, what it says: object of a superclass should be replaceable with objects of a subclass without breaking the app. In other words, derived types must honor the behavior expected from the base types. So over here you see we have interface of bird where we are saying fly, and we have a function where we are making those birds fly, and we are implementing according to the bird. We created a sparrow struct, implemented the fly method. We created a eagle struct, we implemented the fly method, and we are passing it to the function make it fly. But when we implement for penguin is also a bird, but penguin doesn't fly. So we were only handling the case for bird that will fly, but penguin doesn't fly, penguin walks. So what we'll do, we'll update our interfaces, so we'll have both the things, bird and a flying bird. bird that walks, bird that fly. So what we do, we'll implement for sparrow. Sparrow can walk, can fly. We have both the things. But penguin just have walking, not flying. So we'll implement a walk, and we updated the make it fly method with flying bird. Flying bird, where we'll invoke that fly method. You can see we have both the things in flying bird, because flying bird can walk also. So we have a distinction now. We have categorized it more better. Instead of stuffing everything under the same umbrella, we have more distinction. So this is Liskov substitution principle. We are obeying. We are saying that if we'll fly, it will fly. If it's walking, it's walking. We are not saying under the fly, we say it doesn't fly. We'll it walks. So it's not the thing. We have both the things accommodated. Fly birds can walk and fly also, and bird that doesn't fly just walk. We have accommodated that also, but in a two different context, not at the same. Coming to the I of solid interfaces segregation principle (ISP), what it says, a class should not be forced to implement interfaces it does not use. Prefer small focused interfaces over large and general ones. So let's understand this statement by example. Over here, we have a worker interface where we have work and eat. We have a human struct, we define work and eat. We have robot struct, we define work, but robots don't eat. So now, to use this work function, we need to implement eat, and but ideally robots don't eat. So robot is forced to implement this eat method, but that's not correct. So what we can do is have more focused interfaces, divide the context work and eat. So what we are doing over here, we have human, we define work, eat. We have robot, we define work, and we have different functions. Perform work, have lunch. We have humans, robots. We just perform work and have lunch over human. We don't have lunch with robot. We just have perform work. So we have a more focused context rather than a generic one, and as a result of that, we have to implement those methods, which is not correct. Coming to the last character of solid, D, dependency inversion principle. What does it say? High level module should not depend on low level module. Both should depend on abstraction. In short, depend on interfaces, not implementation. So let's take example. So over here we have a database. We defined a save function in that database according to that implementation of the database. Let's say MySQL we have. Now what we do is we inherit that in user service, and when we create a username, we save it in the database. Now let's just say we are using SQL database over here. Now we want to use NoSQL, MongoDB. Now we are kind of logged over here. We are not depending on interface, we are dependent on implementation. Make it in implementation agnostic. What we'll do, we'll have an interface. We just say save. This defines what, not how. Why? For SQL, NoSQL, it will differ. Even for Postgres, MySQL, things are little bit different, or even some new SQL comes, that would be different. So what we are doing over here is we define function for MySQL database save function. Similarly, we create Postgres and we define a save function for it. We basically, we I am skipping that part. We have a struct. I'm taking the thing that you know Go. So we create a method save for this Postgres database. We create a method for SQL database and implement a save method. Now we just include database, a generic type, a database. Over here, you see this interface, a database just defines what, not how. And we invoking the save of that database. Currently, we don't know what database we are using. Over here, we got the instance of MySQL, and then we are initializing, then we are invoking it. Same for Postgres. We initialize, we use, and we invoke. So we are not depending on what type of database. Our end goal is save, not how to save. In MongoDB, it can differ. In Postgres, it can differ. In MySQL, it can differ. Our focus is on what, not on how. This is the end of the video. We have covered most fundamental and crucial design principle: dry, Yagni, kiss, and solid. If you found this video helpful, consider subscribing to the channel, liking this video, and adding a comment. And if you have some suggestion also, please add a comment that I should include in next video. And you have to do what you have to do. So keep grinding, guys. See you in the next one. Bye bye.